In the previous class, we studied the transmission line parameters, transmission line equations, and their solutions. In this class, we are going to study some special cases of transmission lines. So the first one is the lossless line. Here the conductors are perfect and the dielectric medium separating the conductor is lossless. That is, when the signal passes through the transmission line, there should not be any loss. Let me draw a transmission line here. There is a source. It's a transmission line. There is a load there. Now suppose that the voltage available at the input side is V. In the previous discussions, we have marked the voltage at this side as V plus delta V. That is, we have already shown that the voltage at this side is V plus delta V. So there is a potential drop delta V. So for the transmission line to be lossless, there should not be any drop. So the resistance should be zero. So the series resistance capital R should be zero. This is the first condition for a lossless line. And also there should not be any charge leakage. So the conductance, that shunt conductance should also be zero. So the conditions for a lossless line is that the resistance, that series resistance should be zero, and also the shunt conductance G should be zero. And if there is no loss, there is no attenuation. So the attenuation constant alpha can be written as zero. So we can write the propagation constant. Propagation constant gamma is equal to alpha plus j beta. Here alpha is 0, so gamma can be written as j beta. And in the previous class, we have studied the expression for the propagation constant, which is given by root of r plus j omega L into g plus j omega C. So here r is 0 and g is 0, therefore root of j omega L into j omega C. This j omega can be taken out, so j omega into square root of L into C. So that is equal to j into beta. So beta can be written as beta is equal to omega into root LC. This is the expression for the phase shift constant beta. From this expression, we can write omega by beta is equal to 1 by root LC, and this quantity is known as the phase velocity, which is denoted as Vp. So in the case of lossless line, the propagation constant is j omega into root LC, from where we can write the phase shift constant and also the phase velocity. Now let us write the expression for characteristic impedance for a lossless line. Characteristic impedance is R is equal to root of G plus, sorry, R plus J omega L the whole by G plus J omega C, which is equal to root of J omega L by J omega C. R and G are 0 here. So Z0 is equal to root of L by C. And Z0 can also be written as R0 plus J into X0. So here there is no complex term. So Z0 can be written as R0, which is equal to root of L by C. This is the expression for the characteristic impedance. So the condition for a lossless line is the resistance should be 0, the shunt conductance should be 0, and the propagation constant is given by J omega into root LC. So the phase shift constant beta is omega into root LC, and the characteristic impedance is root of L by C. Now let us see the second case, that is low loss line. Low loss line means there is a loss, but the loss is minimum. So in the case of lossless line, we will say that the resistance is 0 and the shunt conductance is 0. But in low loss lines, these elements should be small. It should not be 0. If it is 0, it will be a lossless line. So the elements causing the loss should be small, so that we will write the resistance R, it should be very, very small as compared to omega L, and the conductance should be very, very small as compared to omega C. So these are the conditions for a low loss line. Now let us write the propagation constant gamma is equal to alpha plus J beta, which is equal to root of R plus J omega L into G plus J omega C is equal to root of, see, I'm taking out J omega L from here. So J omega L into 1 plus R by J omega L. Here J omega C is taken out. So J omega C into 1 plus G by J omega C. Now here J omega can be taken out. So gamma is equal to J omega into root of L into C into 1 plus R by J omega L into 1 plus G by J omega C. Now this can be written as gamma is equal to J omega into root LC into 1 plus R by J omega L the whole raised to half, again 1 plus G by J omega C the whole raised to half. Now we can write 1 plus x the whole raised to n approximately equal to 1 plus nx if x is small. So if x is small, 1 plus x the whole raised to n can be taken as 1 plus nx. Here in the place of x, it is r by j omega l. We have already said that for a low loss line, R should be very much less than omega L and G should be very much less than omega C. So these two quantities, that is R by J omega L and G by J omega C, are very small. So this can be approximated using this relation. So gamma is equal to J omega into root LC into 1 plus half into R divided by J omega L into 1 plus half into G divided by J omega C. Now gamma is equal to J omega into root LC, the whole into these two terms can be multiplied. So 1 is multiplied with 1 and half G by J omega C. So 1 plus half into G by J omega C. Then I multiply with this term plus half into R by J omega L plus half R by J omega L into half G by J omega C. See, the last term is so small because we have already assumed that R is very much less than omega L and G is very much less than omega C. So this last term can be neglected. So we can write gamma is equal to J omega into root LC into 1 plus half into G by J omega C plus half into R by J omega L. Now let me write the last equation once again. That is gamma is equal to J omega into root LC into 1 plus 1 by 2 into R divided by J omega L plus 1 by 2 into G divided by J omega C. So gamma can be written as J omega into root LC into 1 plus this 1 by 2 J omega can be taken in common. So R by L plus G by C. Now let us multiply this J omega into root LC inside the bracket. So gamma is equal to J omega into root LC plus J omega into root LC into 1 by 2 J omega into R by L plus G by C. J omega gets cancelled. So gamma is equal to J omega into root LC plus 1 by 2 is there. Let us multiply that root LC inside the bracket. So that is root LC into R by L plus root LC into G by C. Now gamma is equal to J omega into root LC plus half into root of LC by L square. That is, this L is taken inside the square root so that it becomes L square into R plus square root of LC by C squared into G. Or we can write gamma is equal to J omega into root of LC plus half into R into root of C by L plus G into root of L by C. Now This is the expression for the propagation constant gamma. The propagation constant gamma can be written as gamma is equal to alpha plus j beta. So this is the expression for that attenuation constant alpha, and this is the expression for beta. So beta can be written as omega into root LC, and this omega by beta can be written as 1 by root LC, and this quantity is known as the VP, the phase velocity. So now it has derived the characteristic impedance of a low loss line. Now let us try to derive the expression for the characteristic impedance. The characteristic impedance can be written as Z0 is equal to R0 plus J into X0, or Z0 is equal to square root of R plus J omega L the whole by G plus J omega C. Here that J omega L is taken in common from the numerator. So J omega L into 1 plus R by J omega L the whole by J omega C into 1 plus G by J omega C. Is J omega gets cancelled. So Z0 is equal to root of L by C into 1 plus R by J omega L the whole raised to half into 1 plus G by J omega C the whole raised to minus half. And these two expressions can be expanded using the relation 1 plus x the whole raised to n is equal to 1 plus nx if x is small. Here also this R is very small compared to this omega L, and G is very small compared to omega C. So we can expand it like this, root of L by C into 1 plus R by 2 into J omega L and into 1 minus G by 2 into J omega C. Now let us multiply these two terms each other. So Z0 is equal to root of L by C into 1 minus G by 2 J omega C plus R divided by 2 into J omega L plus R by 2 J omega L into minus G by 2 J omega C. Now here the last term, that is this term, can be neglected because R and G are very small as compared to omega L and omega C, so that we can write Z0 as Z0 is equal to root of L by C into 1 plus 1 by 2 into J omega is taken in common, so that R by L minus G by L. Now this 1 by J can be written as minus J. So Z0 is equal to root of L by C into 1 minus J by 2 omega into R by L minus G by C. Let me multiply this negative sign inside the bracket. So Z0 is equal to root of L by C into 1 plus J by 2 omega into G by C minus R by L. Or we can write, let us multiply this root of L by C inside the bracket. So Z0 is equal to root of L by C plus root of L by C into J divided by 2 omega into G by C minus R by L. This is the expression for the characteristic impedance. Now let us compare this equation with the equation R0 plus JX0. So this is the expression for R0, and This is the expression for x0. That is, r0 can be written as root of L by C and x0 as root of L by C into 1 by 2 omega into G by C minus R by L. Now let us discuss the third case, that is distortionless line. A transmission line is said to be distortionless when the attenuation constant alpha is frequency independent and the phase shift constant beta is linearly dependent on the frequency. That is, alpha is independent of frequency and beta depends on frequency linearly. And this distortion refers to the change in the waveform of the signal. It can be shown that for a distortionless transmission line, R by G should be equal to L by C. So this is the condition for a distortionless line, that is R by G is equal to L by C. This condition is actually very difficult to realize in practice. For example, the left hand side of R by G is about 1000 times greater than the right hand side L by C for telephone lines. So it is not so easy to achieve this condition. One of the methods to reduce distortion is to increase the value of the inductance capital L, and increasing the inductance of a transmission line in order to reduce the distortion is called the loading of the line. I'm not going into the details of the loading since it is beyond the scope of our syllabus. Now let us try to derive the expression for the propagation constant in the case of a distortionless line. That is, gamma is equal to alpha plus j beta, which is again equal to a root of r plus j omega L into g plus j omega C. From this condition, we can write the expression for G as C into R divided by L. So I am substituting G here. So gamma can be written as gamma is equal to root of R plus j omega L into G is replaced by RC by L plus j into omega into C. Or gamma is equal to root of R plus j omega L. I'm taking this C by L in common from here. That is C by L into R plus j omega C into L by C. C is cancelled. So gamma is equal to root of R plus j omega L into C by L into R plus j omega L. R plus j omega L is taken outside the square root. So root of C by L into R plus j omega L. Now multiplying this root of C by L inside the bracket, gamma is equal to R into root of C by L plus j into root of C by L into omega L. And comparing this equation with the equation for the propagation constant alpha plus j beta, is alpha can be written as alpha is equal to root of C by L. As we have mentioned earlier, alpha is independent of frequency, and beta can be written as beta is equal to root of C by L into omega L. Or we can write beta is equal to root of C into L square divided by L into omega. L is cancelled, so omega into root LC. And that omega by beta can be written as 1 by root LC and is known as the phase velocity Vp. So these are the expression for the phase shift constant, the attenuation constant, and the phase velocity. It is seen that the attenuation constant is independent of frequency and the phase shift constant linearly depends on angular frequency. Now let us write the equation for characteristic impedance in the case of a distortionless line. Z0 can be written as R0 plus J into X0, which is equal to root of R plus J omega L divided by G plus J omega C. I am replacing the equation. I am replacing G with the equation G is equal to CR divided by L. So Z0 can be written as root of R plus J omega L the whole by CR by L plus J omega C, or Z0 is equal to root of R plus J omega L the whole by C by R is taken in common, C by R into, sorry, C by L is taken in common, sorry, C by L into R plus J omega C into L by C. So C and C are cancelled. So Z0 can be written as a root of R plus J omega L the whole by C by L into R plus J omega L. This R plus J omega L will cancel each other, so that Z0 will give you root of L by C. Comparing this equation with this equation, that is R0 plus Jx0, it is seen that R0 is equal to root of L by C. So we have discussed three different cases, that is a lossless transmission line, a low loss transmission line, and distortionless line. It is seen that except the attenuation constant, the other characteristics such as phase velocity and characteristic impedance of a distortion-less wire and lossless line are the same. Also, the phase shift constant beta linearly depends on omega, since the expression for beta is equal to omega into root LC. That's all about today's class. Thank you.